All right, let's jump right in. Welcome to this comprehensive training guide, straight out of Part 14, Chapter 2 of our Earthing book. I know a lot of you tuning in are students or junior engineers getting ready to tackle some serious, real-world projects, so I've designed this explainer to be super straightforward. We're going to take you from the absolute basics all the way to the nitty-gritty mathematical design. Now, just a quick heads up, we are sticking strictly to earthing today. Lightning protection, that is a whole different beast, and we'll be covering it in a completely separate explainer. Okay, let's get to it. So, here's our roadmap for today. Section 1, why we earth. 2, AC versus DC systems. 3, soil resistivity. 4, the design process. 5, infrastructure. And finally, Section 6, common mistakes. We're going to systematically build your knowledge following the ultimate engineering arc, which is understand, calculate, select, and verify. Every single section builds directly on the last one, which means no skipping ahead. Section 1. Why we earth electrical systems. Look, before we touch a single formula or boot up a spreadsheet, you absolutely have to understand the foundational reasons why earthing even exists in a solar plant. If you don't know the why, the how is just blind calculation. And the why really boils down to two massive priorities. First, personal safety. We earth to safely redirect fault currents away from people. If a wire frays and touches a metal mounting frame, we need that dangerous current to shoot straight into the ground, not through the body of a maintenance worker who just happens to be leaning on it. Second, equipment protection. By giving our system a true, solid, 0-volt baseline, our protection relays can instantly detect when something goes wrong and clear the fault. These 2 points right here, they are your absolute top priorities. Moving right along to Section 2, AC and DC earthing systems. Let's look at how a utility-scale PV plant separates its earthing into two distinct but totally interconnected halves. You aren't just building one giant uniform grid out there. You're actually managing two different types of power. And notice the really strict division of resistance targets we have here. Over on the DC side, so your module frames, combiner boxes, inverter chassis, you're aiming for a resistance of 3 ohms or less. But on the AC side, your transformers and medium voltage switchgear, that target actually relaxes just a bit to 5 ohms or less. But listen, here is the absolute golden rule. Even though they have different targets, both of these systems must, and I mean must, connect at the main earthing bar. That's what ensures equipotential bonding. Basically, it guarantees no dangerous voltage differences can exist between the two sides of your plant. Section 3, soil resistivity, the vital input. Okay, every calculation you do, every single piece of copper you size, it all depends entirely on this one critical environmental variable, the soil itself. We represent this with the Greek letter rho, and I seriously cannot stress this enough, especially to the junior designers out there. Never, ever guess this value. Do not just pull a generic number off Google, because low resistivity makes earthing incredibly easy. But high resistivity, that requires massive, expensive interventions. You have to go out to the physical site and measure it using the Wenner 4-point method. Your entire mathematical model rests entirely on the accuracy of this one field test. And this comparison right here brilliantly illustrates exactly why. Just look at the contrast. If you're building a solar plant in a swamp, your soil resistivity is floating around 30 ohm meters. I mean, you could practically stick a single rod in the mud and hit your safe limits. But if you're building in dry sand and gravel, that number spikes to a massive 1,000 ohm meters. That dry sand literally acts like an insulator. It's going to force you to use chemical enhancements, super deep earth rods, and massive grid arrays just to make the plant safe. Bottom line, the soil dictates your design budget. Section 4, step-by-step design process. All right, now we transition from understanding into calculating. We know our targets, we know our soil, so let's see how the math actually flows. 7. According to the design guide, there is an exact 7-step process that engineers must follow, and it is rigid for a very good reason. Adhering to this ensures total compliance with international standards and, way more importantly, it guarantees safety. One of the most vital parts of those 7 steps is calculating group resistance. You can't just keep hammering rods into the ground an inch apart and expect the resistance to just drop infinitely. No way. There's a geometry factor called lambda that accounts for the mutual interference between adjacent rods. If they're too close together, their electrical fields overlap, and they basically become useless. you have to mathematically calculate the group resistance based on their physical arrangement, and then combine that with your horizontal conductor loop. Let's quickly distill that 7-step process into its biggest milestones. You're always going to start by calculating the expected short-circuit fault current. Once you have that, and you've factored in the physical geometry of your rods like we just talked about, you find your combined resistance. But all this math, it all leads straight to step 7, verify step and touch voltages. This is your ultimate pass or fail metric. You are literally mathematically proving that if a massive fault happens, the voltage radiating through the dirt beneath a worker's feet or the voltage on a metal frame they might be touching will absolutely not reach a lethal threshold. Section 5, Infrastructure and Equipotential Bonding. Okay, let's step away from the formulas for a second and look at how this whole thing is actually built out there in the dirt. How does the theory become reality? Well, when it comes to the physical hardware, your dedicated earth electrodes aren't just any random metal poles you found lying around. They have to be specialized copper-bonded steel rods, or solid copper, typically around 3 to 5 meters long. And notice the redundancy requirement here. You need at least 2 interconnected electrodes for every single PV array block. Why? Because if one connection fails, or maybe it corrodes over the 25-year lifespan of the plant, that second one ensures the system stays safely grounded. And the physical installation itself is strictly regulated to protect this infrastructure. Your grounding conductors, they must sit in trenches that are at least 500 millimeters deep. And you don't just dump the excavated dirt back on top of them. The cables are actually sandwiched in clean sand, 100 millimeters below and 200 millimeters above. This is crucial because it protects the soft copper from sharp rocks and ensures really uniform soil contact. Finally, all of these trenches and cables route all the way back to the main earthing bar, tying the entire plant into one beautifully synchronized equipotential zone. Finally, Section 6, Common Design Mistakes to Avoid. To wrap up this training guide, we really need to review the absolute most common errors engineers make. These are the classic pitfalls that routinely ruin otherwise flawless designs. For instance, a very classic cost-saving mistake is burying aluminum conductors instead of copper. Sure, aluminum is cheaper up front, but installing it below ground is a massive, massive mistake. Aluminum is highly reactive with soil chemistry and moisture. It will corrode rapidly, basically dissolving your entire safety system right out from under you. The correct approach here is totally unwavering. Never use aluminum below grade. Always use copper for your buried earthing grid. And that brings us to the single most critical takeaway from this entire guide. The author explicitly warns us right here. Your spreadsheet math is completely meaningless without physical verification out in the field. You could design the most elegant, perfect 7-step mathematical model in the world, but once that system is actually built, you must measure the actual earth resistance using the 3-point fall of potential method to actually prove that it works. So, armed with this structured approach, taking you from the core basics of safety all the way through those rigorous design calculations, the choice is ultimately yours. Are you ready to mathematically ensure the safety of your next solar plant and, more importantly, rigorously test it in the real world? Use this guide, trust the process, and I'll catch you in our next explainer where we're going to tackle the wild complexities of lightning protection.